Today we will see network topology, which is third technique of general analysis technique. First we saw KVL and KCL, which deals with 1 and 2 variables. Then we saw mesh and nodal, which deal with just 2 and 3 variables. Whereas today we are seeing network topology. This technique can deal with any variables 4 and above. That's why we will see the only arrangement. That's why it is called topology. By this technique, any problem can be solved. For examination, for solving this, it will take laborious time. That's why the concepts are asked in the exam. They may not ask the big problem to be solved, but in IES, this is complete problems is also asked to be solved. Whereas in GATE and PSU exams, the concepts are asked, or small problems or simple problems in the chapter is asked. Some people are neglecting this, some people even do not know much about this. That's not good practice, because we need to be completely ready about the exam. In any exam, we need to see the depth as well as the width. Width means syllabus. Syllabus will decide the width of the exam. That means how many topics to be studied. Whereas the question paper will decide the depth of the exam. So one should prepare keeping the width as well as depth, means syllabus as well as question paper. This is the context we are speaking this topic or learning this topic. That's why this is called network topology. Let's go to in details. The first thing we will concentrate on basic terminology. This is a very simple or general topic. For example, if you go to computers, the same thing definitions are valid. Because when you arrange computers, it's called computer topology. So the topology, let's see the definition. It's an analysis technique having importance to the arrangement of the circuit and without any importance to the type of element or the value of element. In this analysis, we are not interested in type of the element. For example, it can be a resistor, inductor, or a capacitor. We are not much interested in the value of that element also. That's why this is basically deals with about arrangement, and hence this technique is called topology. That's basic meaning of arrangement. The second definition is graph. By using topology technique, every element in an electrical circuit can be replaced by a line. Whenever we draw a line, but not the element, it is generally called graph. For example, in our high school mathematics, we always draw graphs. For example, you draw the graph of human beings. We don't put human beings there. We only put a line. You talk about any other type, we don't put that type. That's why the value is not important, the type is not important, only the arrangement is important. Such a thing is called graph here. For example, if you see at this network, please understand I am taking only one problem to illustrate the total subject. In all concepts I have started or ending with this only. So let's take one circuit having 4 nodes A, B, C, D. These are the 4 nodes that we have. And we have 6 elements here. First element, second element is here, third element is here, fourth, fifth, and sixth. And you also observe there is a direction for this. Each element has a direction. Wantedly, I took the directions, all outside elements are in same direction. And all inside elements are leaving this node. That's how I made it, so that it will be easy to follow. And I also gave the values of each element. If you observe 10, 10, 10. Outer elements I gave like this. Then some elements I gave this way. So when you look at these elements and look at the circuit, and look at this graph. So you see A, B, C, they are the nodes, and each node is connected with a branch. Please look at here, none of these graph elements is signifying the element there. It's not saying what type of element is there, what type of, how much value is there. It is only showing there is a branch. And please observe another important thing. First element is very important. There are two elements, but we still call it as one line. So even that's why series combination of elements or parallel combination of elements between two nodes is always treated as a single element place. So that's why one should understand this concept to say these two, though they are two elements, treated as one. This is called graph for this circuit. The next one, oriented graph. When you see this oriented graph, the orientation we can easily understand. The word orientation means some direction. So whenever there is a current directions given, for that graph we achieved already, that's called oriented graph or connected graph. Because in engineering, particularly in electrical and electronics, electrical, whenever you say the word connected, that means current flows. So to say current, we always use the word called this. So the orientation need not be unique. For example, one can take one direction, other can take another direction. In all the electrical engineering, electrical circuits, we have a standard thing. You assume any notation that you have. If the actual current is opposite, you will get the negative answer. So you don't need to worry about the orientation. One can take in one direction, other can take in another direction. That's a very important precaution or important observation. Let's see the next definition. Complete graph. If the graph contains only one branch between any two nodes, that graph is called complete graph. As I already said, any two elements between the two nodes is called single branch, like here. Any parallel branches available between two nodes is also called single branch. Such a thing is called complete graph. So it contains only one branch between any two. Though there may be a combination of two branches or three branches between two nodes, it is still treated as one. Such a graph is called complete graph. Next one, branch. Branch is a line in the graph which connects two nodes is called a branch. Node is a point of intersection between two or more branches. Preferably, right from the beginning I have been telling, node means a point where there is a current division. Wherever there is a division of current, we will treat it as a node. For example, look at this graph. In this graph, A, B, C, D. These four are nodes. 1, 2, 3, 4, 5, 6. The 6 are 1, 2, 3, 4, 5, 6 are branches. So from now, for the further study, we will say branch and node. That's how I am setting my definitions. Then, degree of a node. A degree can be defined as the number of branches incident at any particular node. That's called degree. For example, look at here. In this graph, take a node A. How many are there? 1, 2, 3. B, 3. C, 3 elements. D, 3 elements. That's why the degree of this circuit or the graph is 3. Tree. It is part of a circuit having no current in any branch but contains all the voltages, all the nodes. So look at this graph. Tree means basically, look at the physical tree that we see every day. In a tree, you will have branches. They will not be connected, just they go. Similarly, in this graph, if I take this as a tree, here no current, here no current, here no current. In examination point of view, these trees are becoming very, very repeatedly being asked. Therefore, tree means the part of the graph which contains all the nodes but no current in any branch. That's the meaning of tree. There are some properties of tree. Please observe as I go along. Branch of a tree is called a twig. Another name for a branch is twig. And suppose if there are n nodes, tree has n minus 1 branches. For a completed graph, number of possible trees are n power n minus 2. It's very important. This question came many times in the exam. So please note this, n power n minus 2. For any graph, number of possible trees is determinant of AR into AR transpose, where AR is reduced incident matrix. I'll be talking about this incident within few minutes. Incident matrix, if you have AR, if you follow this equation, determinant of AR into AR whole transpose, whatever that comes, that is also called tree. But most of the time, instead of wasting so much of time and calculating this, you can simply use n power n minus 2. So this is our properties of tree. So we have seen what is a tree. We have seen what the properties. Properties means how many trees are there, branches are there. Now let me illustrate. Next one is co-tree. The part of the oriented graph is not covered by the tree. Such is called co-tree, and its branches are called link or chords or ties. Very simple. Suppose you have a tree and remaining elements are called links. That's the meaning. Whatever is not a tree branch is a link branch. For example, look at here. If the number of branches are b and number of nodes are n and number of links is b minus n plus 1. This is the equation for number of links. So on this equations are very simple, problems are very simple, but because some people are neglecting this topic altogether, they are facing problem in the exam. So why should we lose the marks when the questions are very simple? For example, let me talk to you about the co-tree. For the previous tree, which we have taken as this one, this one, this one. So if you remove those 3 branches, that is called co-tree. What is co-tree? Tree along with that extra elements is called co. That's the meaning of co-tree. That means tree along with a subtree, like that. So any branches other than the tree is called co-tree. Now I am going to matrices. Please remember very important thing. Why should we talk about matrices here? KVL, KCL deal with 1 or 2 variables. So just with equations we can finish it. Mesh and nodal deals with 2 or 3 variables. There also you can manage with maximum equations. But the very purpose of coming to topology is to deal with higher number of variables. So when you go for higher number of variables, equations, we can't directly solve it. We will put the equations in the form of incident matrix. So when we put the equations in the form of incident matrix or the matrix, so without matrix we can't solve such a big problem. Another serious important point is, in industry there will be more number of variables. So all this KVL, KCL and mesh nodal that we study for examination's sake is not useful for industry because more number of variables are available. Therefore, this topology became very important in the industry point of view. Now let me talk about 3 matrices. First matrix is incident matrix. We call it as A because this is the first matrix we study. It's a matrix which tells the relation between the branch nodes in terms of branch voltages. For example, let me define. What is this matrix Aij? Normally we say Ij, one for rows and one for columns. That is equal to 1 for jth branch currents leaves the ith node. As we have been following in KCL and nodal analysis, whenever the current is leaving, we are calling as positive. Same notation we take here. Whenever it is entering, we call it as negative. And we say 0 if it is nowhere connected. So, looking at these 3 simple definitions, we are going to go with the meaning of or how to achieve incident matrix. Now I will illustrate with a problem. Let's call this as problem number 1. Incident matrix for the graph given. What is that? For example, this is the graph for us, and this is a node we have, the branches we take. The node is A. So what are the elements that are linked to A? Please observe here. Into this, into A, 1 is entering, minus, 2 is entering, minus, 6 is leaving, plus. Please observe here. A, 1 is entering, 2 is entering, 6 is leaving, 3, 4, 5 are nowhere connected this node. So that's what the meaning of it. Similarly, if you take B, look at here, 3 is leaving, 4 is leaving, 5 is leaving, all are leaving, so we should put plus 1. Please observe 1, 1, 1. Look at C here. 4 is entering, minus 1, 6 is entering, minus 1, 5 is leaving, plus 1. Therefore, minus 1, plus 1, minus 1. Last, look at D. 1 is leaving, plus 1, 3 is entering, minus, 5 is entering, minus. So 1, minus, minus. So one important precaution is, so though I have entered all this here, there is a very interesting precaution. Sum of each column is 0. Please observe here, minus 1 plus 1, 0, minus 1 plus 1, 0, 1 minus 1, 0, 1 minus 1, 0, 1 minus 1, 0, 1 minus 1, 0. So very important observation is, sum of each column is 0. Whenever sum of each column is 0, that shows the total circuit is considered. This application is very interesting. You see, look at the properties. Sum of each column elements is 0. Determinant of incident matrix of a closed loop is 0. If the row of the incident matrix of a reference node is omitted, then the resultant matrix is called reduced incident matrix. As I mentioned earlier, AR is a reduced incident matrix. Good. So having looked at this, let me back to incident matrix here. This has a very interesting application. For example, Chief Minister wants to talk to collectors. He also follows this topology. Any company owner want to talk to their people being spread over different places, and he will check whether all the computers are connected. As I said, this topology means just an arrangement. Arrangement can be of computers, arrangement can be of people, arrangement can be of anything. It need not be electrical circuit. That's why, and you look at this, when before that VIP starts video conferencing, he will check whether every column has become 0. If any column is not giving 0, that means one particular person is missing or few people are missing. Then he will stop the video conference and he will wait till the incident matrix shows all columns are 0. So that's a very important application nowadays that being followed. Now let's go for the second matrix. The second matrix, I am introducing it as tie set matrix. The very word I am using tie. Tie, as I already said, it's a link. So if you take a tie here, that's called linking. So tie is another name for linking. So it talks about branches that are linked. It talks about currents. So incident matrix talks about branches, how they are incidenting on a node, whereas tie set matrix talking about currents, because tie means a link, link means closed, closed means current. We deal with currents. And let us see the matrix we say. This matrix gives relation between currents to the oriented graph. I am calling it as a B because this is second matrix. Bij is 1 if the jth orientation in the same direction in the ith loop direction. I mean to say, it talks about loops as I mentioned. Every link make a loop. Please remember one word. Tie set makes current. Cut set breaks current. Tie makes current, link makes the current by linking. Cut means by cutting no current. So in tie sets we deal with currents because current is flowing. In cut sets we deal with voltage because it is cut, no current means voltage is there. So here also I am talking about three things. It is positive one if both are in same direction. What are the both? Jth branch current, loop current. You are going to take a loop current and we will check each branch current in that. If they are in the same line, we say, if the same direction, we say +1. If they are in the opposite direction, we say -1. If the branches are not at all part of that particular loop, we say 0. So that's how the topology or the second matrix deal with. Let me illustrate with a problem. This is our second problem. Second problem is to tell how to make this matrix. Look at here. The loops we are taken here, the branches we are taken here. Please observe this is loop 1, loop 2, loop 3. Loop 1, look at another important observation. This dark line is tree. This dark line is tree. The dotted line is links. So if you see only dark line, there is no current. By connecting 1, there is a current here. By connecting the branch 6, there is a current here. By connecting branch 5, there is a current. That's why 2, 3, 4 is called tree. 1, 6, 5 are called links. Now we are trying with tie set matrix, that means link matrix. So we should consider the dotted lines. For example, this is first dotted line. This is first tie for us. How to take the loop direction? Loop direction is same as link direction. Look at the one direction, then I took the direction in this way. So please remember, once again I am telling, the link direction is important as taken as a direction. Here also sixth direction is taken. Here also fifth direction is taken. So in every orientation we are taking 1, 2, the first one here, second loop here, third loop here. Please observe now how I am going to enter into the matrix. Suppose you talk about first loop. What are the elements linked in this loop? 1, 2, 3. So you will have entry only for these three elements. All other elements will have 0 because they are nowhere connected. So that means only 1, 2 and 3 you will have entries. All other elements you will not have entries. Look at this. 1, same direction, +1. 2, opposing, -1. 3, same, +1. Observe here, 1, -1, 1. So 4, 5, 6 are nowhere part of this loop. So please observe how I am entering this loop. Secondly, when you come to second loop, I have taken the link direction as the direction. So what are the elements linked here? There is 2, 4, 6. Now for the second loop you will have entries only for 2, 4, 6. But the question is how? Answer is simple. For 2 you have 1. For 4 you have -1. For 6 you have +1. Why? This direction is taken, so 6 is in the same direction. 4, if you see, loop direction, branch direction is opposite. Please observe this arrow. Then this is in the same. So 2 will have +1, 4 will have -1, 6 will have +1. Last loop. When you take the third loop, which direction do I take? As already said, I will take the direction of link branch. So fifth branch is here. So this is the direction. So this will be positive. Opposite with this minus, same as this plus. So 5 is +1, 3 is -1, 4 is +1. Observe this, -1, +1, +1. This is called tie set matrix. Please understand one more thing. Just like the previous incident matrix, sum of each column is 0. Here it need not be equal to 0. It need not be equal to 0. By mistake it comes or by chance it comes, don't worry. But don't search for making every column as 0. So that is about tie set matrix. These are the properties. Tie set is a set which contains loop includes only one link. In each, preferably one link is there. Then what's the direction? As I said, the direction of the loop current is the link current. Then number of ties, how many? Number of links. If you can take more also, but that will unnecessarily increase the complexity of the problem. Already in topology we are dealing with high number. But please understand, we have to deal with more than 4 variables. But for illustration and for examination, for academic purpose, I am taking still 3 variables. Actually 3 variables you can deal with mesh and nodal. But I am taking this to illustrate. Otherwise, if I take a big one, it will be very difficult for you to understand, difficult for me to tell. So sum of each column, as I mentioned, need not be 0. But what is the direction of it? The first element or the link element will decide the direction. So that's all about how to achieve tie set matrix. Now I am talking about the last matrix, that's called cut set matrix. For convenience, we call this matrix as Q. What is the definition? It is a matrix which gives relation between branch voltages. Please remember, tie set deals with currents, cut test deals with voltage. What is it? Qij positive if jth orientation is same as ith current. -1 if it is opposite. 0 if it is nowhere linked. Same as previous. Just instead of current you take voltages. Instead of loops we take nodes here. So please remember, I am going to take illustration as a third problem. So coolly observe this third problem. For convenience sake, for you to concentrate more on the concept than on the circuit, I am maintaining same circuit in every problem. Same circuit in every problem I have taken because you will be able to focus more on the technique than on the circuit. So please take the same circuit and graph also, the tree also same. Look at 2, 3, 4. Thick line, as I told you, this is tree. Dotted line is links. As I told you, tie set matrix is with the dotted lines. Now I have come to cut set matrix. In cut set matrix we deal with tree branches, that means thick branches. Look at, for example, this is 2. With 2 we are talking about node 1, cut set 1. You know why it is called set? It's more than one branch, please remember. In the previous, in each loop there are 3 elements. That's why it is not one element, it's not one branch, that's why it's called set of branches. That's why the word came tie set. Here also cut set. Cut is basically talking about voltage. Now look at this, we call it as voltage. See the arrow, and there in the tie set we have taken the link as a arrow, reference for our direction. Now we don't have any direction as such, it's called potential. Look at this, for example, if you take the second one, you can take here. If all these directions are going, you see, the direction of 2 is the direction. Now what is the elements here? If they are leaving, suppose this is entering. So this A you can treat it as negative. Take this 2, minus is there. The potential of A is called negative. You know why? Because current is entering. Current can always enter into negative. So because current is entering, we can say or assume this as negative potential. Now 2 is entering into negative, accepted. 1 is entering into negative, accepted. But 6 is leaving That's not accepted. How can the current leave from negative? That's why this, if 1 is entering like 2 is entering, same, positive, positive. Whereas this is leaving, when this reference is entering, this is entering, both are positive. But this is leaving. That means when the reference is entering, 1 is leaving, we should put minus sign there. Now please look at this graph and look at this one. 1 entering, 2 entering, 6 leaving. Therefore 1, 1 minus. When the main branch is entering, 6 is leaving. That's why opposite. You see there? These two are opposite. These two are same. This is coming in. This is coming in. Plus, plus. This is leaving. Minus. Now come to the second loop. Second node. Look at here. With respect to 3, I am taking here. This is all down. Same direction means you can say plus. Take plus. Leaving minus. And here fifth one is also entering. So like 3 is entering plus 1, 5 is entering plus 1, 1 is leaving. When the main thing is entering, this is leaving, you should say minus 1. So please observe my table here. So this is why we have to take how these are connected here. So 3 is plus 1, 1 minus 1, 5 plus 1. So in this cut set, what are the elements? 1, 3, 5. So these 3 elements will have entry, all others are 0. Next, look at the third and the last one. This is node C. What is the direction? This is the direction. Why should we take this direction? Because our element is 4. Fourth element is a tree. So thick line, as I told you, tree branch we take 4. 4 is going that way, positive. 6 is also going that way, positive. 5 is going in the reverse direction, negative. You see there? 4 is plus 1, 6 is plus 1, 5 is minus 1. So like this, we can have a cut set matrix. Cut set matrix, you follow the arrows. With this 3 matrices done, 90% of the chapter is over. And tie set, cut set is more important than incident matrix. Please remember, incident matrix is to understand whether the circuit is complete or not, connected or not. But tie set is to calculate the currents and voltages. And cut set is also to calculate voltage and then currents. So you please observe how I will be using these matrices to bring a beautiful conclusion. Then only you will really understand the very purpose of these matrices. Otherwise, you do not really understand why we are studying all this. Now let me take you further. These are the properties. Cut set divides a graph into 2 separate graphs. Every cut set contains only one node. The orientation of cut set follows T. As I said, tree branch will take as a node. So these are the properties. Now I am coming to fourth problem. Again, same circuit, please observe. This problem, from now the things are very simple. Impedance matrix. It's a matrix deal with impedances of each branch, but that is diagonal matrix. Please observe, all elements are connected in diagonal. So let's talk about first branch, 10. Second branch, this is first branch, 10. Second branch, 10. Then third branch, 10. Fourth branch. Like this you can have whatever the values in each branch, you can always calculate. Then when you look at the admittance matrix, whatever you have done there, you can do 1 by 1 by 1 by. So admittance matrix is exactly reciprocal of impedance matrix. Good. Then sixth problem. Voltage matrix, current matrix. Voltage matrix we call VS because it's not simply voltage, it is voltage source. V for voltage, S for source. So there are 6 elements. In each element, how many voltages are there? If you observe this graph, you have elements only for first element. That's why we say 100. All elements are 0, 0, 0, 0. But there is another important thing. Shall we put plus 100 or minus 100? You need to put plus 100 because it is going from positive. Please observe here, positive, current is leaving. Positive and current is leaving, it is same direction, plus 100. Now next thing is current matrix. Current matrix is what are the current sources in each branch. If you observe this, in no branch has current source, please. So that's why I have put all zeros in current matrix. So voltage source matrix has first branch has voltage, current source matrix no branch has current source. That's why zeros. So these are the simple matrices that I have formulated. Then I'll show you how to solve it. Then what are the nodal voltages we have? We have node at A, node at B, node at C. Though why not we take this one? This is treated as reference. When we treat it as reference, we say 0. That's why though there are 4 nodes, we take only 3 nodes. It's called nodal matrix. Nodal matrix for voltage. The next one, link matrix. What are the links we have? Are the loops we have? First loop, second loop, third loop. So 3 loops, loop currents, 3 nodal voltages. And if you observe how I am going to use this, please observe this table. This table is giving the climax. And I need to connect all the things I taught so far, and you need to really observe all that you have learned. Let's carefully and with patience understand this. For example, here B, ZB, B transpose B. What is B? B is basically tie-set matrix, as I told you, is equal to B into Vs minus ZB into Is. Very easy to remember. This is Vs, so Z into I is also voltage. And from this, the only unknown is IL. You will be calculating IL. So from this matrix, we will be calculating loop currents. Similarly, after getting the loop currents, that means IL from here, you know B is already done, tie-set matrix, ZB impedance matrix, then Vs source matrix, Is current source matrix. Actually, in this problem that I have taken for illustration, this becomes 0 because Is is 0. Similarly, having got IL, please come with me to understand IB. IB means branch currents. Branch currents is B transpose plus IL plus Is. That means whatever you got here, use here. If you use this one, you can estimate branch currents. From loop currents, branch currents. From branch currents, what do? We get branch voltages. So please observe, IL, from this one IL comes, from this one IB comes, from this one VB comes. If you calculate and see all that, it should be 0. That is the check. You can check whether your solution is right or wrong. This is based on KVL. That's why please remember, KVL became mesh, same KVL became tie-set matrix. Similarly, cut set. KCL became nodal, and nodal means voltage, voltage means cut. So let us see the cut set how is doing. Exactly same as we studied there. Look at here. For example, in the place of B, you got Q. In the place of Z, you got Y. Place of B, you got Q. So in the place of loop currents, we have 3 voltages. And follow this from here, calculate the 3 voltages, nothing but nodal voltages. So link currents will come here. Here we will get nodal voltages. That's why I say tie-set is like a loop current and mesh analysis. Cut set is a nodal analysis. Having got VT, substitute here HEVB. Having got VB, substitute here HEYB. That's why loop currents will give branch currents, branch voltage. 3 voltages will give branch voltage and then branch current. If you check this one, it will become 0. That's why this is a check for KCL. So this is about how I brought all the matrices that I taught so far into this and finally achieve. The main target of any problem is branch currents, branch voltages. So we can achieve branch currents here and branch voltage here, branch voltage here and branch currents here. Now let me take you a few more problems before I end up the lecture. Ninth problem. Related to the given fixed tree of a network, we need to find out what are the options. Link currents from an independent set, branch currents from an independent set, link voltages from an independent, branch voltages from an independent. See, look at all these options we have. The option is A. You know why? Branch currents we don't talk as far as a fixed tree, we talk links. Link is a current. So link and current is the word we need to take. Branch current we are not interested because branch current comes from link current. Link voltage we never talk. If at all we talk about voltage, we talk about nodal voltage or tree voltage. Link makes current, no, so we don't take voltages. That's why the best option would be A. Let's go to 10th problem. Identify which of the following is not a tree of the given figure. Look at this figure. He has given ABCD. This came in gate 99, 1 mark. You may wonder, 1 mark, such a big circuit, no problem. What are we seeking in this problem? He said, which is not a tree. That means, find out the options given. Wherever current is flowing, call it as not a tree. Because tree means no current. As I've been telling, tree breaks the current, link makes the current. So he is asking for tree. What should we say now? If anything is making a loop, understand that's not a tree. So therefore, answer is C. Let me show you why it is C. Look at here, A, D, H, G. I am showing you in the figure. Please observe, carefully follow. One is A. A is here. Next, after A, this is D. Next, H. Next, G. What happened? Can I show you what exactly happened? A, D, H, G. That means what? Closed. Anything that is closed is a tie but not a tree, is a link but not a tree. So the option is, I am taking this option because A, D, H, G is acting as closed. Closed cannot be called as tree. That's it. Then let's go for the 11th problem. The graph of electrical network has n nodes and b branches. The number of links with respect to the choice of a tree. This is a very straightaway problem. I don't know why he is asking any simple equation. Very simple, because as I told you in the previous theoretical lecture when I was giving concepts, I already said this. L is equal to B minus N plus 1. Therefore, option is A. I am repeating again. B minus N plus 1 is the answer. Straight answer, A. Now let's go for 12th problem. The number of cards in the graph of the circuit. How many cards are there in the circuit? As you know, the option. Number of cards means number of links. Just now, one exam. In one exam, he asked the equation. In another exam, he is asking the numerical. That's all. As I told you, he cannot ask a bigger things because in objective exam, such a big topology cannot be asked, but he's checking. That's why you see, gate 2008, it is given for 1 mark. Can I give the answer? Very simple. How many branches are there? 1, 2, 3, 4, 5, 6 branches. How many nodes are there? 1, 2, 3, 4. So B minus N plus 1. B is 6. n is 4. So 6 minus 4 is 2 plus 1 is 3. Therefore, answer is 3. A is the answer. 13. The network has 4 nodes and 3 independent loops. Very interesting. What is the number of branches in the network? This is given in IES 2007. He is again asking you to check this answer. Very simple. Simple equation. L is equal to B minus N plus 1. Can you observe I am showing the solution also. Look at here. Number of branches, links or loops. B minus N plus 1. He said number of links are 3. B we have to calculate now. He also said number of nodes are 4 and plus 1. So this is 3 plus 4 is 7 minus 1, or you can say this is minus 3. This minus 3 goes outside and becomes 6. Therefore, this equation he is asking again and again. Now I am asking a simple homework or self-preparation. What is it? Repeat the above problem by use the problems whatever we had discussed by using KVL and KCL. What I am saying is I have done with topology approach that has taken a laborious one. This is just to illustrate and face the exam as well, get ready for industrial problems. But the same problem you can solve with KVL and KCL or measure nodal. If you solve with measure nodal, this may come very faster than topology. But the only difference is topology can handle higher number of variables, measure nodal will handle lesser number of variables. So these are the different approaches to show. Therefore, today I am concluding one of the very serious, biggest, toughest topic called, important topic called General Analysis Techniques. As we have been telling, this General Analysis Technique means any technique for any circuit. So have these 3 approaches, get ready for all the 3 approaches, you can answer the questions well. So KVL, KCL, measure nodal, tie set and cut set. These are the 3 different techniques under the heading of General Analysis Techniques. You can apply, solve any bigger problem starting from 1 or 2 variables for any number of variables. This gives completeness to the topic called General Analysis Techniques. Then for next class we will be starting a second important topic called Specific Analysis Techniques. Exactly opposite to this discussion, where specific means specific technique for a specific circuit, whereas so far we studied any technique for any circuit. Therefore, we will see there how we are using theorems, how we are using different specific techniques involved, and that is also there. We will be starting second important